In this video, we're going over a few rotational problems that we didn't get to in class. And this first one is asking us to rank the rotational kinetic energy of some hollow spheres. And they are all rolling without slipping. They have the same mass, but they have different speeds and different radii, which is misleading because they are all drawn like the same size. So as we look at these, we could calculate their radii pretty easily because we are given velocity and omega. But let's look at the equation for rotational kinetic energy. So when we look at that, we know that that would be 1/2 I omega squared. It's just like 1/2 mv squared, but remember we're always using I instead of m when we do these rotational things. So I looked up the value for I in the book, and for a hollow sphere, let me find the page. It's, I believe, 2/3 mr squared. And with a lot of these things that have, a radius like a disc, a cylinder, those have some fraction times mr squared. And so you're going to see this pattern a lot where it's got the fraction multiplied by the mass times r squared. Okay, let me pause. Okay, found it. So on page 274, I'm getting from the table here the about its center of mass, because that's what we do when we're doing rolling without slipping. We have a thin spherical shell, and that would be I equal to 2/3 mass times radius squared. Okay, so we know that the value for I is going to be different for each one. So then let's substitute that in. We're going to put 1/2 times 2/3 times the mass times the radius squared. We still have omega squared in here, which we know that value for each sphere, but I would really like to either solve for the radius and plug that in, or let's see if we can get rid of the radius because I know that omega is equal to v over r. And to me, it looks like we're going to be able to get rid of radius completely. So if we do, I could simplify this too. That doesn't matter. It's just not changing. So I have r squared here. I have the quantity v over r squared. Great. Then I'm going to get that the rotational kinetic energy is 1/3. The r squareds are going to cancel, and I'm going to have mv squared. That gets it in terms of v, and without the r, which I hadn't solved before. So now I'm just ranking it. Since the masses are all the same, I'm ranking it in order of greatest to least, with E and F first. Then we see it goes the 50 ones, B and D, and then C, and then A. Okay, let's go on to the next one. For number 14, we're comparing all of these objects and what portion basically of their energy is going to be in the form of translational kinetic energy versus rotational kinetic energy at the bottom of this ramp, because we want to know which one's going to get there first. And so we know, for instance, that they all are going to start out with the same, well, one of them's got more mass, but they all start at the same height, and then they're going to come down to the bottom with a combination of translational and rotational kinetic energy at the bottom. So when we, for instance, if we take the 2 kilogram solid sphere, okay, we're going to have 2/5 times 2 kilograms, okay, times its radius. They all have the same. Okay, all 4 objects have the same diameter. Okay, so they all have the same radius squared. Ooh, I am totally plugging in the wrong thing in the wrong place. So here, this goes over here. 2/5 r squared. That's just the I value though, right? So then that's times 1/2 times omega squared. That's that term, plus final energy. And then for that particular rotating object, that solid sphere, then it's going to have mass times g times h. Okay, if I keep going here, let's plug in, it's going to have 1/2 mass velocity final squared here. And then I can put in, for instance, I can cross that out. Well, maybe we should save the 1/2 and deal with that later. Okay. And then this, again, notice I could do V over R here because it's rolling without slipping, squared. So in this way, I'm looking and comparing all these objects to each other. Mass is going to cross off here. So I'm not worried about the fact that the 2 kilogram solid sphere and the 1 kilogram solid sphere, they're going to be the same as each other. So then it's a matter of the thing that has the most rotational inertia is going to have a greater portion of its energy locked up in rotational kinetic. And it's not going to get rolling, right? Literally, as fast. And so it's going to have a greater portion, bigger I here. And more of its energy will be tied up in rotational. Less of that original potential energy will be translational. It will have a lower final velocity. And we can go through a proof of this in class. So we're basing it off of the higher inertia objects are going to be slowest. So that's why we're putting mr squared at the end and the last, that's the hoop. We're putting the sphere, the solid spheres, which have a smaller fraction, 2/5, first. And they're tied because mass cancels. Okay, for this one, we're trying to fill in the bar chart. And I'm confused because it did say qualitative, but then they proceeded to do some numbers with it. So that means it's quantitative, doesn't it? But anyway, so when we are solving for this kind of problem, we're trying to get translational and rotational kinetic energy all in the same term, so we can understand like how much proportion of each is there in this rolling hoop or disc or sphere. Okay, so then when we're looking at this situation right here, we have initially, that's where we're at, it's already rolling. We know that for this translational, that would be KTI, let's say. That is 1/2 mv initial squared. And we actually have numbers, right? So we don't have the mass, I don't think, but we know the translational velocity. And then the rotational is for a thin hoop, then you would want to go look up the information. Again, this is on page 274. So for this one, you're going to go look up the I value if they're asking for it to actually like be quantitative. So for a hoop like this, it's rotating about its central axis, about its center of mass, we're saying, and that is mr squared. So this is, and then we don't want to leave it in those terms though. We would like to have it in terms of, instead of r and omega, we're going to put it in terms of initial velocity. So then let's put that in. So we have 1/2 mr squared times omega squared. But hey, that's great because we know that v is equal to r omega for things that roll without slipping. So then, this means that this is, if I group this part together, that looks an awful lot like vi squared. So then kti and kri are equal in size, is what we're finding out. So that's why they drew this one the same size as that one. And then all of that energy is gonna become gravitational potential, because when it rolls up the ramp and comes momentarily to rest, it's not only stopping. When you think about it, it's both stopping, like it's not moving up the ramp anymore, and it's also not rolling anymore. And so you want to be sure about both of those things before you leave. Like, for instance, both of these are blank. Okay.